Alright, I think I have this in place where I want it. Let me open up things here.
My two companions both ended up almost dead.
Is that a reflection on you or them?
Mostly just luck because I had a friggin' fire giant helping me. And fighters just do a lot of damage.
Fair enough.
Yeah, it was a pretty cool quest. We had to fight a group of fire giants and one was helping us. And hellhounds.
Alright, so here's where we're at. We have finished talking about everything I want to talk about in Chapter 3. I am now moving on to talking about Chapter 4. Your next batch of homework is going to be combined Chapter 3 and Chapter 4. I find Chapter 4's... We'll probably talk about it today and start programs on it on Thursday. There won't be as much discussion as the different switching. And I've tried to introduce things on Chapter 3. So I will get those programs up this week. I wanted them up this weekend, but I didn't. And I'm not going to cry about it. I'm still grading your Chapter 1 and 2 programs. People will start seeing grades trickle back as I go through and run those. So we'll get this in a good place. Come here. But Chapter 4 are mathematical functions, and it's a little aside. We're going to be using what's built into Java. Let's see, that's in that place. Oh, that's me. I don't want me. Let's see here.
Yeah, I'm struggling with those.
Where did you go? I think that's the one I want. Yeah. All right, good. All right, let me see if I can get these on the...
For some reason, I can't even access my textbook anymore. I bought a digital version.
Did they give it to you on Pearson E Plus or on Vital Source?
It was Byte.
Brightwave?
Brightwave, yeah.
Yeah, that usually gives you a link back to give it access to Pearson Plus. So yeah, I kind of have to do like a double login on it.
Yeah, I inputted the access code to access both my textbooks. Logged out and logged into another device to see if I could get those on my tablet. And no.
I would
Never
contact Pearson support and see what's up with that. Nothing I can do on this end about that.
Brightwave?
No, Pearson. If you've logged into Pearson and you had access on Pearson, then this is up on Pearson's end. I think what I'm going to do is I'm going to turn off this light
Pearson.
and I'm going to turn the back light on.
I wasn't
If this is
Pearson.
too much, let me know. Is that okay?
Yeah. I wasn't on Pearson, I was on Brightwave.
Oh, well then until Brightwave gives you another access code that you then have to put into Pearson to get access to Pearson, shouldn't get the books themselves in Brightwave.
Yeah, because I bought it from the Colette bookstore app, and then I got a code. I put the code in, and it just straight up disappeared.
Yeah, it's a two-step process. It's a pain in the ass with Follett right now. But the code that you get, you put into Brightwave, they'll give you another code that you put into Pearson, and then you have access to Pearson. All right, so we are going to begin to work on objects. This is really our intro to objects, and we're going to be using a class that's built into Java called Math. And I kind of showed this to you. See if I can do it here. When I came in and I said, hey, what am I going to say here? I just want to, if I do math dot, and it showed me that this was a class, and we got to see the different library functions that were in here, and what they can take and what they can output. We did this when we were looking at random variables. And so this is a collection of different functions that are built in to Java so that we can access routines over and over again. So we have a sine function for sines, we have the hyperbolic sine, square roots, and different numerical methods that are usually a little bit longer to code.
I'm still trying to log in. Just give me a second.
I'm Not doing any code right now. I'm just showing what the library functions. And so there are things we can access in Java that we can use over and over again. This is a common with programming languages to build up math routines that we can use. So let me go here. Where did you go? Here. So that is the math class. Whenever you need to use a math object, if you start typing the capital M-A-T-H, you will get a list of them. We want to look at some common usages that we might get for these things. So the first one that I showed you was there are constants. There is a constant for pi, and there's a constant for Euler's number E. So instead of, remember back when we initially were using pi, we said we could make a constant of our own pi, give it as many decimal places as we wanted. The pi built into the math class will give you a double precision on pi. It'll give you as many decimal places as you need for a double. So when you're doing things with circles, you can just reference the math. All right. So if I wanted to do a double area or an area of a circle, now, and I'm going to give it a radius. Sorry. Area will equal, well, we already had the math.pal, so radius squared, right? Remember math.pal? This would square my radius. And then I'm going to multiply that by math.pi. And now I have good built-in functions that are better than, how many decimal places in pi do I want? So this is what we get with these libraries. And doing it this way is we get better precision on our mathematics, and we don't have to watch constants. And like I said, we've already used the power function when we were doing
in
the
chapter
tables.
3 now, right?
4.
Oh, 4. Okay, I'm going to download that.
I'm not sure if I have the files up yet or not. I'll double check. So these are the two main constants that we get in there. E is Euler's number, which E is equal to 1 plus 1 over n to the nth power as n goes towards infinity. That ends up being 2.718, blah, 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 blah. It's a very important number in statistics. Normal functions, bell curves, get centered around a value of E. So E also gets used a lot in probability theory. Poisson probabilities use E. Differential equations are completely based off of this one number. Banking interest, population models, they all use E as an exponential. It's also a function, so as a number, it's E, and as a function, it's exp for the exponential function. So, weird thing, right? Pi's just a number, E's both a function and a number. And we will see some of these in our population models. And then outside of the constants, there's some methods. So we'll have trig functions for sine, cosine, tangent, exponential methods for E, their inverses, which are logarithms, how to round a number properly. We'll get rounding methods on here, so we don't have to just cut off things, right? Remember, we transfer something to an integer and it was cutting off the decimal place. Now we can round to exact decimal places. And how we can find minimum, maximums, absolute values. Very common mathematical functions that, if we think about it from a programming standpoint, take some meticulation to do programming-wise. So they get built into these math classes.
I'm seeing a lot of the crossover with my statistics class.
Yes, yeah. Well, statistics as a science highly benefits from computation. The dealing with a large number of things and the particular numbers and functions and probabilities that are used in statistics, they're really hard to calculate. Z scores, actually figuring out what the Z number are some of the hardest integrals I've ever seen in calculus. Mm-hmm. But once you program them into a computer, you get a number out of it. So computers has helped with some of that, right? We don't have to worry about these crazy integrals. All right, so in trig functions, we have the sine, which returns If you give it some number, it will output the sine value of that number. Cosine, which is the cosine function, and we have the tangent. Now, all of these mathematical functions are done in radians, not degrees. So when I do the arc cosine, or I want to know what the angle is, or to go backwards, it will give me something in radians. So we have these functions where 2 radians turns the degrees into the radian value. So, when you get to pre-calc or and you start doing your unit circle, your radians and degrees are interchangeable on these. But the computer will use radians because they're unitless on it. But we human beings, we like talking in degrees. So a lot of the time with these functions, we'll have to use a 2 radians. I'll say, hey, I want 90 degrees. Well, I need to turn it to 2 radians, and that will turn it to pi over 2 for me. So those are the trig methods in there. I don't think we do a couple of trig functions with the cosine of an angle and the sine of an angle with some of our but I think that's in section 5 when we build some methods. Exponents. So there's a function e to the power of, which, let me make sure I have this in the right place. Yep. If we talk about interest, right? If you get a loan and you get interest on it, the interest accrues. Continual interest accrues such that your principal is equal to the amount, your initial amount, times that weird number e to the power of your interest rate times time. E was a number invented by bankers. It became a lot more useful. But so what this EXPAA does here is this as a function. It takes, so if I were to code this on a computer, I would say that what I owe on the loan would be a double principal. And let's say I'm just going to put a double for all these variables. I'll put initial amount, I'll put my rate, and I'll have my time in years. Right, so they're all doubles. Right. So if I want to know what principal is, how much I owe on my loan, or how much I'm going to pay back, because the banks always need to make a profit, I take the initial and I multiply it by the exp function with the rate times time given to it. So that's how an exponential function would appear in there.
Okay.
So this does e to the power of something. Now e has an inverse, which is the logarithm. This is a problem between computers and calculators. If you look at your calculator has 2 keys for logarithms. You have an ln, an log, and if you shift above it, this will be e to the power, and this will be 10 to the power.
I didn't know that.
Old mathematics, this was called log, and this was called log10. Somewhere around the 60s, they changed it, and they started calling this the natural log because of how important this number was. And so most calculators have ln and log. But computers have log for the inverse of that, and they have log 10. That's a legacy of how language has changed. So we see this here, where the natural logarithm, or which you'd use on your calculator to be ln, is just plain old log. And then in log base 10, which is on your calculator, is plain old log. You have to type the 10 in. Now, what I liked about this is most of you are going to be using computers consistently. One of the things you should start trying to do is some of the things that you might have seen in your math class. Compute on the computer. It's useful. And it gets you used to the commands on the computer. We've already been using power, so we could have a double A, which is the base, and to whatever power we're taking it to. So when we did our radius squared, we put our radius in here, and we squared it. We also have the ability to take square roots. So these are functions that are built in. So let's see. If we keep track of what we have things to do things with trig, which historically were really damn hard without computers. That's why you see computers advertise that they do trig functions. If you ever look at trig functions pre-calculators, you had to have a book of tables to look up all the values. You had to use slide rulers. These things are not easy to calculate. Computers, and really your calculator is just an ancient fucking computer, right? It was, hey, we can do these math things really quickly, and now they've been made obsolete by the better processors we have. So you get a huge advertising on the trigonometric functions because they were something that were really, really hard for people to do without computers. So a lot of computing problems go to the things that you can't do by hand. So right. Trig is important on that. Exponentials are the same. When you're taking the power of something, if I'm looking at, I want to know how pH is affected in water, and I'm talking about the actual ion concentrations, I'm talking about 10 to the negative 5.761. Well, how do I figure out what 10 to the negative 5.671 is, right? It's a hard calculation because I need to multiply 10 over by something, right? I don't know how to do that by hand, but logarithms and exponentials give us the ability to do that.
Yeah,
so
like that would be very hard to figure out.
Well,
without a calculator.
Again, there were ways to do it by hand, but they were very involved. And because they were very involved, as soon as calculating tools came about, these were some of the first things put into calculating tools. Which is why when you get to the math section in a computer course, you're going to talk about the things that are very, very hard for people to calculate by hand, but are easy for a machine to do. And some of the examples we're going to do is, hey, here's this thing. You try doing it by hand. Yeah, it sucks. But you let the computer do it. And, hey, there's your number. There's your answer. Right? Because that's how these tools end up getting used. And then in rounding methods, right? I've already told you to be wary. We've added 0.1 to a number until all of a sudden we got this extra little bit in the end that we had no clue where it came from because computers don't do fractions accurately. So one of the things you need to do is you need to control what your doubles are. You need to round whenever possible. And so we have some functions that can round in a couple different ways. So in general, there is more than one way to round. We're taught that if I have 3.5481 and 6.5987. If I want to round to this decimal place here, we look at the number to the right, and if it's less than 5, we drop it. So this would become 3.548 because this is less than 5, so we drop it. If I'm rounding to this decimal place, this is bigger than 5, so I increase this by 1, 6.599. Notice that rule system that I said that, right? That rule system is a whole bunch of decisions. So we build these into functions into the computer, so we don't have to make these decisions every time we do this. The other thing is, well, this doesn't work in all cases for rounding. In some cases in rounding, like in statistics, because that 5 is preferred here. And what ends up happening is I get numbers that are slightly pushed closer to, let's see, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So with the 0 digit here, I actually get numbers that are pushed towards the bigger number. So the bigger number will get an extra 0. And so there are some statistics where they ask you, well, if this number is even, if you get 5, round down. If this number is odd, get 5, round up. There's extra rules. So there's more than one way to round based on what you need. If you need your numbers spread properly, or what you're measuring. And so that's what we see here, are some different ways of rounding. So what ceiling does is it takes whatever your value is and makes it go to the ceiling of the next integer. So I'm going to erase up there. I'm going to just keep using the board space for illustrations of these things. And ceiling and floor are probably two of the things that I use the most in computers that I never expected to. Because they force how I get rid of decimal places. They force how the number is going to act. A ceiling function, so this is my output, and this is my input when I have a ceiling function. So if I have any number between not including 0 and 1, my answer is 1. Any number not including 2 or not including 1 up to 2, my answer is 2. So what happens is if I'm here, if I have 0.35, I round it up. Not a 5 rounded up. I'm bigger than 0, so I push up to 1. I push up to the ceiling. So if we can think of the ceiling and the floor here, if this is 0 and I have a small value bigger than 0, I immediately push up to the ceiling. It becomes the larger number. And so it creates this weird little ladder. Well, floor is the opposite. It says, you know what, just throw away the decimal places. So if it's 0.0031, I'll throw away the decimal places, it becomes 0. If I have 1.286, well, I throw away the 286, it becomes 1. And so the same idea, I'm moving from the ceiling to the floor. Well, the floor function says, well, I was at 1, but I didn't make it all the way up to 2, so you're down to 1. You fall down to 1. And so there are ways of just chopping off the decimal places, but they're going to tell you, should I have moved up or should I have moved down? So here is rounding to the nearest integer. So if x is equally close, so it sits at the 0.5 between the two, the even one is returned. So if I'm 1.5, I'm going to go up to 2. If I'm 3.5, I'm going to go up to 4. If I'm 2.5, I go down to 2. I return to the even number. Right? So that's what RN does. So 3.4 takes me to 4, or takes me to 3, because that's the nearest. So this is your normal rounding. Except when you're at 0.5, RN is normal rounding. All right, so 3.4 rounds down to 3. The only difference between normal rounding with RN is if you're at a 0.5, you move towards the even number. Right? Not always up, not always down. You just go to the even number. Int round is the rounding you're used to doing. And what that actually does is it takes the floor and adds 0.5 to it. And then it chops off the extra bit. So it shows you how that works. But int round is the rounding you're used to. Right? So if I add, so let's say my number was 3.4. Right? Normally I would round down to 3. Does that make sense? How we can do that is, well, if I add 0.5 to this, so 0.4 plus 0.5 is 3.9, and now I convert it to an integer, So I drop off the decimals. That's how the computer does it. It adds 0.5 to it. So if I were at 3.5, I would end up being at 4.0, and I chop off the decimals, and it rounds. So that's the trick the computer does to do the rounding that we know how to do. But it's built in for you. The rounding we know how to do is just called round, and the book's telling you, hey, this is how the computer does it in the background. Does that make sense? And then we can round doubles also. And they do the same thing. They convert the doubles, because they're bigger than integers, need a long on them. And this is just the size of the number. I think a couple of you, when you're doing the population models, I think you hit a few numbers where you scrolled over, you got negative numbers when we were doing an in-class example because you filled up what the integers or the doubles could do. So if your number, or what your floats could do, if your numbers get really, really big and you need to round, we use double to long. Same process though. We'll get some examples here. All right. Other functions we have and we can return is I can find which of the two numbers are larger than each other. What we can do with this is we can end up using it to sort things. And that's going to be our big goal here, is we're going to want to sort things. You're going to see that we're going to talk a lot mathematically, and we're going to slowly turn that mathematics into generalizations. I can talk about characters on the keyboard as if they're numbers, and early in the alphabet is smaller than later in the alphabet. So sorting numbers in order can end up being the same as alphabetizing words. A lot of the tricks with the computers are turning things that aren't numerical into something that we can do numerical operations on. Because they are a computer, they tend to just compute. So right now we're looking at how we can do some math functions. In Chapter 5, we're going to turn A and B into letters. And which letter is bigger than the other tells you which one is further in the end of the alphabet than the other. So a lot of this mathematics becomes a transformation. Absolute value gets rid of the sign. So absolute value of -2 is 2, right? Absolute value of 2 is 2. It tells us how big the number is. It doesn't tell it gets rid of if it's bigger or less than 0. And that's helpful for when we need to deal with certain parameters. And we've already been using random, right? We had that program where we made a little bit of a flashcard using random. We got some numbers between 0 and 1, and we played with adding and multiplying to it to get the numbers we wanted on it. And we're going to continue to play with random numbers because that is one of the key things that helps us with computers. All right. And yeah, character types. Sorry, today is a definition heavy day, right?
Yeah. I know.
Thursday we will program a little bit more with these definitions. I'm not sure. I might get through the definitions. We might see one program today, and I apologize for that. I did warn you that kind of the pattern is Tuesday's a little lecture heavy in the first half of the course. Thursdays are a little more play with the computer, but some chapters, like 3, we play more. And we're going to try to get through all the definitions in 4, and then we'll play with it more later in the week. We okay with that?
Yeah, I'm having a hard time keeping track of all these definitions, so many of them.
Well, we do have paper, and you
Yeah.
can have pencil to make notes, and processing things through writing can sometimes help your brain on that.
Yeah.
The neuroscience of that is really weird. So your optical recognition extends at the end of your optical nerve. Recognizing characters actually happens before it hits your brain.
Really?
And how you imagine brains actually sit in the front, really close to connected to where your optical nerve is. So when you imagine something, you're imagining there, you are almost literally seeing it in your optical nerve. Now they found when testing people with reading and writing and definition skills, people that write by hand have a larger vocabulary, and people that write by cursive have a larger vocabulary. Cursive, because the letters link together, you're actually building recognitions of letter patterns, and writing in general, you're imagining word constructs in this part of your frontal lobe. When you move back further and you are just reading and just seeing, you lose the imaginative part of it. And something about how we learn, all of those levels blend. And so some things are better to learn actively by doing. Some things are better to learn to write out the steps and then go back to the steps.
That's how I learn. I learn by doing things.
Well, what they have found is people have preferred learning methods, but they might not be the best for every type of thing. So for mathematics, for me, I'm very visual. I need to graph mathematics.
Yeah, that's fair.
But for history, I need to write things in sequential orders and tell stories out of them. And one of the best things you can do is to use different learning methods for different subjects and to switch them. Because
You history buff too?
Pardon?
You're a history buff too?
No. I've had to go through history courses to get my degrees. And they are stories to me, where mathematics are pictures to me. Not saying that I haven't learned some mathematics by learning the history of like how we get from complete the square to the quadratic formula. That's a story in mathematical words. So I use as many modes as I can. It's just interesting the psychology of how we learn.
Those are also like interesting, like deep dives into like how the mathematical formulas came around.
I'm not sure if it's deep dives. You need to do it to get a degree in mathematics.
Yeah, it's interesting. Like,
so we're going to have a data type that represents characters. Now, I think what is this? The American Standard Characters List 2 is what ASCII stands for. Initially, what happened was when computers first were encoding data, and people needed to put symbols on them. There wasn't a standardization between machines. And this, like 1940s, 1950s, very first computers, hey, A is going to be 1, B is going to be 2. In data, oh no, we need the numbers to be 0 to be 0, 1 to be 1. Oh no, we need the space to be 32, right? Where you put this translation from that weird character you had to how you stored it in memory, because the memory has to be a number, was different between computers. IBM and a couple other companies early on recognized that data was going to need to move from computer to computer. So they made a standard for characters. And what happens is that if I look at these, and you don't have to type these in, but I'm going to show some of these to you in Eclipse of looking at character, is this represents one word, one byte. And that byte translates to a table of letters. The table is fairly arbitrary, but there were some things they did in the table, like they put capital letters and lowercase letters separate, and they put them in alphabetical order. So A is a lower number than Z. And that worked fairly well for English-speaking countries, so Australia, England, and the U.S. and Canada.
yeah.
But there are other characters coming out. And
Isn't New Zealand one of those too? I know that's like.
yeah. I didn't mean to offend the Kiwis, but you're right.
I'm not.
No. You ever confuse a Kiwi with an Australian, they'll be upset at you.
Oh, yeah,
and it's fair to not ignore them in what else isn't Kenya dominated by English because
I don't know.
Yeah, Kenya, I think English is the major language in the schools there.
Is.
If England owned it at one point, there's a large chance that it has English as its speaking language.
That's true.
But that doesn't cover everything. So they later came out with a 2-word system called Unicode. And Unicode actually works in hexadecimal. So this is 2 words here. What do I mean by a word is 2 bytes. So these 2 digits tell me the first word, and these 2 digits tell me the next word. But it's in hexadecimal, so I can my characters are from base 16. So
New Zealand's on my bucket list for vacation someday.
So hexadecimal has 16 base characters to the number system, and their values are the same. up until you get to A.
I didn't know that.
Well, because computer words were 8-bit and 8-bit, a 16-base system was useful for the first 16-bit systems, and so 16-bit systems. So what ends up happening? How many people have used web stuff before? You ever do color in web, where your RGB color, let's say if you wanted to make something completely red, was FF0000, right? So you have an RGB color, which you need.
I mean, I have screwed
This
around
is
with
0
access
through 255. This is 0 through 255. This is 0 through 255. Tells you how much blue, how much green, how much red. Okay. Well, a full 255 is FF in hexadecimal.
I mean, I have screwed around in a hex editor before.
Then you've seen hex.
There was like a glitch in a game, and like someone told me like if you shaded one line of code, it fixed it, and I did it. It worked. Yeah.
Well, what a hex editor does is look at the memory in how memory is encoded. So if I wanted to encode, let's see, RGB, red and blue, a purple, right? That's how we would encode it in web. What it did is it reduced the number of characters you needed to talk about what was stored in memory. Because memory only needed to store 0 through 255. By enforcing it to be 2 characters for this, right, that means 255, 0, 255. Notice how, right, I'm missing 2 characters there when I talk about the 0. And if this value was lower, right, am I missing 4 characters? By enforcing it to be some values that perfectly fill memory, I can always guarantee that I have the same character length. So when I read these things in, they're very easy to translate. And the same thing happens with our letter coding here. Unicode uses hexadecimal to make sure that we fill these 4 spaces perfectly, and we can access every part of memory on it. Well, let's see if I still have it here. All right, yeah. So I'll see if my Eclipse still shows this here. Do I have my Unicode here? Yeah. Let's see. Oh, that's not the one I want. Somewhere in here. I'll try to find it. Well, let's see if I can do it here. Let's look at string inputs. Strange characters. All right, so let me work with this here and show you some hexadecimal. All right, so I'm going to input a char value. I'm not going to work with a string right now. I'm going to make a char.
I'm gonna try this. Strange characters.
I'll start it this way.
Java util scanner.
I'm not going to slow down to show things here. I'm just using this illustratively. So
Yeah.
let's see here. Make sure I have everything I need here.
I'm just doing it myself because that helps me learn it.
That's fine. I just want to show the values themselves coming up and through.
Yeah.
All right. So I have a char value and I have single quotes in this. And so I'm going to show you what's in value. Okay? So it prints back out the char because this is a char type. But let's play with this and peek inside of it. I do apologize. Again, I'm just trying to show you how these things are under the hood. Okay? So, let's see. Plus. I think that'll do what I want. So, the char itself, because the computer sees this as a char type, when I use it, print is going to translate that to what the character is. Okay? But char is stored as an integer in memory, and the value of capital A is 65. So what I'm going to do here is I'm going to make a little chart of chars for you. Give me a second here. For integer I equals 0, I less than, I'm going to go up to 255 because that's the first two words, okay? And char character integer value. Alright, so I made a little for loop that's going to count from 0 to 255. If I didn't type everything wrong. Let's see here. Oh, I need an I here. Thought I typed the I. There we go. Okay, so what I'm going to do is I'm going to say that character equals I. And I'm going to print out. Let's see. I'm going to print the number first. I plus space equals 1. And then character. Check that right. Oh, I need. Plus, and then I'll put a space on the end. And let's see. How many? 1, 2, 3, 4. I'll do 5. Let's see. I'll do 8 characters per line. So, if I is divisible by 8, then I'll print a blank line. I think that'll do it. I might have made a small mistake in here. We'll fix it as we go, but hopefully we'll get a chart. Oh, no, I had an error. What did I screw up? Probably typed something. Oh, let me convert this to char. Let's try that. Still giving an error. Boom, 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 boom. Unresolved problem, type mismatch, convert from integer to boolean. So I made a boolean mistake here somewhere. Input, so let's see, integer is value. I don't need integer. I is less than 1. Oh! No, that's fine. I equals 0. I plus plus. Print equal, I. If I mod 8. Here it is. That's what I didn't do. Let's try that now. There we go. Sorry about my little typo there. But this is what the computer actually hides a table at underneath. So 0 is actually a new line. 1 doesn't have any representation in Eclipse when you get these weird, I don't know if you've ever played with Microsoft stuff and you get the weird 0, 1, 0, 1, 0, 1s.
Binary.
No, what's happening is this is giving me a number in Unicode and telling me it should be the Unicode character here, but it doesn't have the font for the Unicode character. Right. Have you ever seen this before in Word or other things where you get some weird symbols? Yeah. Sometimes in Notepad you get like the weird circles and question marks. It's because the number it has, it doesn't have a font for. And these first few areas have some weird special characters in them. And you'll see in the appendix of the book it has your ASCII. I remember, and I said it distinctly, 32 is a space. Remember when I said we'll make 32 a space? That's really where ASCII started. So what happens here is you have a new line character at 0, and then you have some special system characters. If I remember correctly, one of these, do you remember the old computers would have that bell sound, a beep bell sound on the keyboards? One of these characters is actually to make a sound. So they all map back to something. In memory, it's a number. When it gets processed to the print screen function, it can be a sound. Yeah. Starting at 32, we get a space, and then we start getting the things across the keyboard. So you see the exclamation point in memory, and exclamation point is 33. Our asterisk is 42, and here we go at 65, we get A. And notice, the thing I've been telling you about how we're going to start thinking about processing is A, B, C, D, E, F, G, H, I, J, K, L, and all the way up to Z are in order from 65 to 90. So they've been ordered. Then there's some extra spacing through here, and starting at A equals 97. Well, why did they do that? Well, they wanted to space these evenly. Remember, I'm doing everything by 8 bits here? 8. And remember how I said these count in 16s and 8s?
Oh,
so they made a shift here of a multiple of 8. So that you could shift back and forth by just multiplying.
So the lowercase numbers appear in there too. I mean letters, I mean not numbers.
Yes. Yes, and they're shifted by an even multiple of 8. Notice how they're trying to put math in the background here, so when they're working with these things, I need to go from uppercase to lowercase. Well, I can shift down by an even multiple of 8. Because that's how the numbers are working in the background. Granted, you're going to have utilities that let you use these things, but I just want you to know what it's doing in the background. These things are stored as numbers. And so if we keep scrolling through...
How far do they go?
Well, I only went up to 255.
They go a lot higher.
Yeah. Unicode is 216-bit words. But we'll work on that Thursday, because I think there's 1.6 million characters now on the full Unicode set. What is for...
I see like lots of Greek letters there.
Where's Greek?
Like beta. I see beta, at least.
Where's beta?
223.
Oh, yeah. Well, and we have thorn, right?
Oh yeah, that's a Greek one.
No, that's an old English thorn.
Yeah.
With th sound from like medieval time period. We've got the symbol for yen. All rights reserved. Cents, pounds, copyright. And so there are different characters that got added. This was the initial ASCII table, though. Only went up to 255. And so it doesn't have everything. We've got accent symbols, and this really expanded to the European language set. Right? You can do German, Spanish. Don't think you can do Cyrillic. Cyrillic and Greek were not able to be done in these completely, but you could do German and Spanish and Italian, anything that used the accent symbols. Right?
Okay.
So the accent symbols were added. Of course, again, that still didn't cover the world. So that's where Unicode.
You see the symbol for mu. That's one you see a lot in statistics. It's constantly in there.
Well, yeah, me. Mu for me.
Yeah, exactly.
Where's mu?
181.
Yeah, for mu. next to a new paragraph symbol.
Oh, is that what that is?
Yeah, and then the power of 2, the power of 3,
Yeah.
greater than or less than. So there's patterns in here and there's reasonings for them. But let's see if we can get some Unicode in here.
Yeah, some really weird.
So what we want to do is look at the possibility of doing Unicode. So let's come through here. Come back to here. So the Unicode format will use a /U, and so in this format of Unicode, there's 65,536. But the new Unicode standard has doubled this length, right? And you have languages. I apologize if I get it wrong, but I think in standard Chinese there's 2,000 characters, right? That you need just to represent standard Chinese.
That's a lot.
Well, and there's you've got we have Malaysian text. So Unicode was a way of expanding this, and a way of adding tables that would translate everything back to their formats. Let's see if we can. Let's see. We'll do 65,535. Well, I want to do these in Unicode. So let's see if I can get a full Unicode here. So let's take this up to 65,535. Wish me luck, right? This is going to go for a while here, and we might get a lot of things that don't display. I like the fact that the computer is a little more quicker than I expected it to be. Expected it to go really, really slow.
There's another. No, it's not yet.
So here we have an idea of what we can see. Yeah, that's I took a little bit of Japanese. That looks like it's kanji. Right?
Yeah.
Kanji characters have.
Yeah, I recognize some of them.
And then what do we have? We have some impact fonts. We have Arabic. Right.
Hebrew in there.
Yes, the Hebrew is in here.
Yeah.
Again, I don't have some of the fonts installed. This is what happens when your software doesn't have fonts installed. More Arabic. Let's see.
Wow, there's a lot of.
There's
stuff.
Hebrew.
Yeah.
More. Here's standard Chinese. Which translates over to Japanese because they borrowed some characters from there also.
Yeah, it didn't surprise me. I know Korean too.
Let's see.
I know there's some overlap with Korean written language too.
Don't know. Never studied any Korean.
No, I just know that from history class. Could have sworn I saw somewhere there's like 10,000
Well, that's
Chinese characters.
So
Only
that,
like 2,000 basic ones.
that's Ru. Yeah. So here's more kanji.
Yeah.
So you have character sets now. So this is how we've made computers accessible to the world. Is that we have a mapping that takes a number and maps it back to a character, and that translates from every computer. Every computer that gets built that agrees to the international standards uses these translations. What ends up happening for software is as you switch languages, it takes filters and takes the things that you're entering in one language and filters the characters over. So because they're numerical and these are grouped together in filter sets, they can use multipliers or shifts to move your keyboard across, to move your displays across.
Oh, I see.
Have any of you accidentally ever changed your language in the software on your phone? Right? So there's whole tables that relate things back and forth between the languages. But because the computers agree on a numerical background for the display, they will display. Does that make sense? So, but notice how all of these things are numbers, and why my heavy focus on mathematics? Because even when we get to processing words, at the core of it, it's a freaking number. Everything your computer does is a freaking number. It's not because I'm a math teacher and I like math. It's more probably because that I like math, I ended up using computers. right? They may
Right.
make it easier, but everything these things end up doing, we have to understand the numbers to some extent in the background. So that's why we focus on math functions. All right, so yeah, we've got a lot of characters that, but we have a large world with many languages, and going from 255 things that just seem to take care of white people across Europe to something that can take care of the whole world is a good adaptation for the computer. And being able to translate and use these things functionally is part of what we need to do as programmers. All right, let me close this out here. Let me get this through here and come back. So we can talk about this new data type.
Oh, you're using OBS.
So we can talk about these data types by calling them a number. And the character data type is a translation number. And so here we can see some things that are not printable, right? The carriage return, the form feed, the line feed, tabs that we can pass off as numbers. We also have escape sequences. If I need to add a tab into my printout, I can use a slash or an escape sequence to tab. I can use a control, a slash n to go down a new line. I noticed some of you, when you were first working on tables, you had found these from other things, and now we have kind of a definition from them. We can print to the screen things that we don't have a way of typing. We can either put in the Unicode number or the ASCII number, and it will print to the screen that, or we have these special escape sequences to do that. And so this is going to let us add characters into our outputs. Well, I can count tabs now. Instead of counting 20 spaces over, I can make the computer do tabs by putting /t's in. And here is, I think this is only part of Appendix B, which is what I printed out. These were the things that didn't have a printable. So a null is completely blank. Where's the system bell? I had one student that was trying desperately to get his computer to go ding, 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 ding by hitting the system bell, and it doesn't work on the.
That's sad.
No, it works on the computer directly if you're in the computer directly, but it doesn't work on the. Oh, there it is, 7th bell, right? So you can make a system bell for it. It doesn't work on the virtual server, and so I think, and here would be the hexadecimal codes for them. The table of hexadecimal codes, and this continues down, right? They only showed you the first few. I went all the way to the full 255, so I could make a hexadecimal values of these. We'll play more with converting to hex a little bit. So, I can convert a character to its integer value, but just by declaring it as an integer. Right? I can force it by using typing. Right? By putting this parentheses in first, I'm saying take this character and turn it into an integer, but the Java compiler will intelligently do that. The same thing as if I let it equal a character equal a number raw, that's the same as forcing it to be the character. If you noticed in my code, I tended to use the force, the type forcing. And I said, hey, take this number and turn it into a character. That way, later on down, the compiler will recognize this as a character.
Use the force. I just thought of that.
These, because they're numeric, you can look at a character, and if it's greater than A or less than Z, well, remember how these were put in numerical order? So if I'm asking if a character I typed was greater than or equal to A, capital A, and less than or equal to capital Z, this is actually saying, are you an uppercase letter? Because the numbers are hanging in the background, all my uppercase letters were, 65 through 84, 83? So what this is actually comparing is the thing I typed in, the character I typed in, is its number value between 65 and 83. That means it's an uppercase character. So we see them as different things. the computer translates for us. Does that make sense? And why numerical values work here. Here, then, I can do the same thing with, is it a lowercase letter? Here I can look to see if I typed in a number. Notice I'm giving you ways here. This example here gives you a way. Let's say you want a user to type something in on a menu, right? To type 0 through 9, right? Like you're typing a telephone pad, right? Instead of using a case statement, did you type in a 0, did you type in a 1, did you type in a 2, you can look at the character values, because they're all clumped together and in one statement, validate that input. Does that make sense? Yeah. All right. I think that is, because I want to, okay. All right, we will start with the, I'll talk about the methods in the character class. We will start with strings on Thursday, and we will start programming with strings and characters and numbers. So this is what we're going to do. We're going to ask the user to type in things, and we're going to look at it. We're going to say, is it valid or not valid? We're going to shift things from uppercase to lowercase. We'll tear apart strings. All right? That's really what we're moving through here. But the last thing I want to do is I'll end the character class, and then we'll begin with strings coming across. All of those comparisons I did get put into functions. So is it a digit? If the character I'm looking at is 0 through 9, this returns true. That was the same as this is if statement here. So what they did was they built in a function that says, hey, did you type in a number? Is it a letter? This checks if you're an uppercase or lowercase letter. Are you a letter or a number? See how we're just adding those if statements together and saying, are you lowercase? Are you uppercase? Two uppercase and two lowercase and two uppercase. It takes whatever your characters were and shifts them to make sure that they're always going to be uppercase or lowercase. Now, what that looks like, give me a second here to calculate properly. 0, 2, 4, 8, 16, 32, 64, 128. So, that's where capital A started. See how it was a neat pattern of 8 multiples? I had a 1 bit in the 64 place, and I had a 1 bit. So see how it's starting the 64th power to 1. Oh. And as I moved my way across, so let's see, A, B, C, D, E, F, G. What did we say? I had it back here. Hold on. Let's just make this. Like 100. I don't know what the last one was. So, capital A started at 65. Where did lowercase a start? Oh, maybe that was back a bit. Ends at 93. Let me go back to 32. ABC. Yep. Let's show. 255. There we go. 97. So let's see. 97. So if uppercase A starts here, well, 97 is there. That's lowercase a. So do you see how shifting between uppercase and lowercase is just changing 1 bit? That's the trick they did by doing that. So now your software only needs to see the value at 1 bit. You don't need to do comparisons. You don't need to add or subtract. You look at the 1 bit in memory, and if it's a 0, it's uppercase. If it's a 1, it's lowercase. And if you want to change it, well, let's say I'm changing to lowercase. You look at this, and if it's a 0, you switch it to a 1, and if it's a 1, you keep it to a 1. which you can do with an OR statement. That's how intuitive and what they built in to these systems was to make it look at the individual bits on the tables, so that when you do shifting of letters or shifting of these functions, it doesn't have to think hard. Because for a computer, a switching of a bit is a passing of one comparison. If I need a comparison of a lot of values, that's a chunk through memory. Does that make sense? On how they did that? So we look at the value underneath it all, and that's why I said they moved it a multiple of 8. What it did was, there's only one bit you have to think about now on it. And so uppercase, hey, the 32-bit is 0. Lowercase, the 32-bit is 1. If you need to change it, you just change that bit. Flip one switch. Which is mentally what we do when we think of uppercase, right? It's the shift key or not the shift key. All right, that's all I have for the functions here. We will start with strings. Read chapter 4. I will try to post the homework for chapter 3 and 4 because it is a combined. Because you want to use those math functions and we'll be using strings and characters on them. Questions, comments, queries? Sorry about just weirdness. We'll make it work. Right? I want more hands-on classes and less lecture classes. We're just going to get a chapter where I can dump the chapter in one day, and then we can play on the chapter the next day. 5 won't be like that. 5 will be like 3. It'll be broken up into a couple parts. Okay?
That's the day.
Have a good one.
Oh, it's still 54 out.